In our last video, we explored one of the most fundamental shapes that appears all throughout nature, and that being the circle. And we talked about how this simple shape puzzled mathematicians, philosophers, and natural scientists for thousands of years, trying to understand why was it so prevalent, why did it keep popping up in the physical world, and if we were going to use information to describe it to each other, what would be the least amount of information that we could convey? And we figured out in the last class that especially when we're consulting a coordinate plane or Rene Descartes' Cartesian coordinate system, there's really only two pieces of information that we need to convey whenever we're talking about a circle. One is we need to talk about its center, and the second is we need to talk about its radius. And if I can capture both of those, I am able to tell anybody for any plane how to draw the exact circle that I'm thinking of in my mind. Now, today we're going to talk about probably the second most prevalent of shapes, which is the line. And the reason why it's so prevalent is because, of course, it feeds up into most of the other shapes that we're familiar with. It feeds up into rectangles and squares and triangles. We can use it to draw trapezoids and a variety of other shapes that appear throughout nature. Not only that, but we can use it to describe trend, we can use it to describe direction, and so it's no wonder that lines became incredibly prevalent when ancient astronomers were watching the heavens, as well as when people were starting to explore and navigate into oceans and across vast countrysides to be able to get from one place to another. The lines were incredibly important, and there's, again, only two pieces of information you need to know in order to be able to accurately describe a line to somebody. You need to know, first, a point that it goes through, and the second is you need to know a direction that it's traveling. If you have those two pieces of information, you can describe any line that you were ever thinking of to anyone. In fact, as a fun little riddle, if you were trying to describe how to build a wall to somebody, similarly, you would only need to have two pieces of information. You just need to have where at least one of the bricks is going to be laid for that wall. And the second is that you need to have a direction. And if you have a point that that wall is going through and you have a direction, you will be able to build the wall that you're specifying. That is, of course, assuming that it's just like a line and that it goes on forever and ever in that direction. But when we're talking about lines and we're talking about all these different areas, let's see if we can start to capture this idea of a line in the Cartesian coordinate system that we've been playing with so that we can describe certain details to each other with it. So let's first write down what it is that we're able to kind of logic through. We'll start from a place of philosophy with this. The first piece of information that we know for a line is that, again, it has a point. There's at least one point that I need to know on my line in order to be able to describe this to somebody else in an attempt to be able to write it down. And the second thing, again, is a direction. Now, for our purposes in this class, we can limit our idea of direction down to a little bit of a simpler idea, because we know that we're going to be drawing something what we call in the plane. And in the plane just means on our paper or on a flat surface. We're thinking of this as being a two-dimensional shape. So when we're talking about direction, we can actually talk about this a little bit more simply as slope. Now, when learning about slope, I want you to think about where you might have heard the word slope before. For me, it brings up images of a ski slope. And if I'm thinking of a ski slope, I might think of the steepness or the shallowness of a ski slope. And I could think about how it would be very steep if it was going downwards. Because if it was going downwards, that would be that it is going down a certain amount every little bit that I go along it or across in the direction, forward, I'm going down a certain amount. Similarly, I could think of that as being kind of like steps, a whole bunch of these tiny steps, right? Where I'm taking a step down and across and down and across, and steep steps would be ones where I have a lot of downwards for every step that I go across. Similarly, I could think of a positive slope or a slope that grows as being one where I could imagine having taken these little steps to get to the exact same location as my line, where again, it's going to be steeper if I'm going up quite a bit on every step, and if I'm going across very much on every step. You may think of what another image that comes to my mind is if you've ever watched Ace Ventura: Pet Detective. For the second one, there's a a scene where Ace Ventura is climbing up some ancient Tibetan temple stairs, and these are of course stairs that go almost straight up and are incredibly steep, and so for those there's quite a lot of rise to a very little run, and so those are the kind of stairs that if you're trying to climb them, you know, it requires quite the workout. But if we wanted to talk about very shallow steps like the ones you might have in front of your house leading up, those are going to be ones that go up very little and have quite a lot of run for the little bit of rise. So we get this idea of kind of rising and running as we move from left to right, and we can use that to describe our slope. So in our slope, we'll commonly be referring to slope as this relationship to rise and run. And so as a little bit we're just going to talk about it in one way versus the other. So let's talk about slope as being this relationship of this rise to run, this steepness of stairs that we could kind of talk about. So if I had a hill, this straight line, and I'm trying to relate it to these stairs that are going to act as my reference point for how much I'm going up and over. We could think about going up to going over. If I'm going over more than I'm going up, then that's going to be quite shallow, and if I'm going up quite a lot, then that's going to be quite steep. And so this relationship of up to over is what is often referred to as a relationship of rise to run. Now these are informal math words, so we'll try to take a moment here where we try to contextualize this a little bit. By rise, what we really mean is how much are we going up in our y. So this would be our change in y, which is going to be our vertical change, right? Because vertical, our up and down, is what we've been calling our y axis. And then I've got my change in my horizontal. This would be my change in x. And so we're going to refer to this change in x as our run, and we're going to refer this change in y as our rise. So another way you could think about this rise to run would be that our rise is going to be trying to find the difference between our two different y values on points of this line, and run would be the difference between these two x values for points of our line. So let's, for example, let's take a look at that. Let's suppose that I had a point right here and I had a point right here. And I can give these some numbers if we wanted. We could say that this one was 3 over, and maybe it was 5 up, so that would be 3 comma 5. And we could say that this one over here was maybe 1 over. Maybe it's only 1 over, and 1 up. We could say, how much is my slope? How much am I going up to how much am I going over? Well, for this example, I'll keep it in pink. I'm going to be going up from 1 to 5. So you can think of that as 5 minus 1. And then that would be over the difference in the x values. That's that I'm going from 1 to 3. So I'm going a difference of 3 minus 1. That would get me 5 minus 1 is 4, and 3 minus 1 is 2. So that gets me a ratio of 4 to 2. Okay. Is it important that I look at, what if I accidentally wanted to read it this way? What if I wanted to say that I wanted to go this direction? No problem. Since we've still got our reference plane, it actually doesn't matter, and I'll show you why. Let's go ahead and say that now we're going to do it in reverse. Maybe y2, maybe we'll call this one y2. This will be our second point, and this will be our first point. So y2 would be 1, y1 would be 5, so subtract 5, over x2. x2 would be the x value for point 2 would be 1, minus x1 would be the x value for point 1 would be 3, and so that would get me 1 minus 5 is negative 4. Oh, looks different. But 1 minus 3, there we have it. 1 minus 3 would be negative 2, and so negative 4 over negative 2 gets me a positive 2, which is the same thing as 4 over 2 for this one. So it actually doesn't matter, so long as we're talking about positive and negatives to help us keep our mind straight, and so long as we're organizing this to say that we have to have one point's coordinates directly above the other one, then we're always going to be talking about a proper difference. So there we have it. This slope is really just our ratio of saying that I'm going up a certain amount to how much I'm going over a certain amount. And this makes sense because if I expected to have a large number in my slope, so we could say a large slope, and I'm just talking about the size of the number, not necessarily the sign, so we could say a large absolute value is going to correspond with steepness. This is going to go along with steepness, where I'm going up or down quite a lot. Steepness, as you're reading it from left to right. And here we have, if I had a negative value is going to correspond with me going down as I travel to the right, so down and right. The other way of thinking about that is up and left. right? Because that's going to be down would be my negative y values, and right would be this way. So it would be a negative rise over a positive run would get me a negative slope. So here we go. If the slope is negative, or if the slope is large, and then I'll leave that to you. What do you think it's going to mean if its slope is positive? A positive slope is going to look like what? You got a couple pictures here. See if you can reference those and find out. Now let's take a look at some of the different lines that we can draw when we're given just little bits and pieces of information. So here we are, sketch a line with a slope of m equals 2 over 3. Now if you're ever in a math problem and you're not able to understand exactly what it's talking about, take a minute to understand the context clues. Here, sketch a line with slope m equals 2 over 3. So m is meaning the slope. So that's just the title that we're going to give slope is the letter m to help kind of talk about it more succinctly. Now, if you're curious as to why that is, Duke EDU actually says that there isn't quite a consensus on why the letter m has been chosen. A couple of interesting points. Some people believe that it might be talked about the modulus of slope. In other words, the number for slope is why we use the letter m. But it is also interesting that some other people claim that it's because the French word for to climb is monter. And so here you have maybe a little bit of residual reference from René Descartes and those who were studying alongside him. So here we have the slope, regardless, is going to be called m, and we'll be using the letter m to talk about slope. Okay, so we have a slope of 2 over 3. Let's think of all the different lines that we could draw with that. Okay, well that's only one of the pieces of information we need in order to draw a line. The other is a point that it goes through. So let's maybe first choose a point. I'll choose the origin. Why not? The origin's a perfectly good example for us to try. And so here we are going to interpret the slope. Remember that the slope could be thought of as rise over run. But if you wanted to think of rise, really what we're talking about is a change in y values. Okay, so it's going to be a change in y over a change in x, which we could think of even more simply as y2 minus y1, my changing from y1 to y2, over x2 minus x1, my change from x1 to x2. Okay, so I'm going to be changing my rise by 2 every time I change my run by 3. So let's go ahead and interpret that. I need to change my run by 3. Okay, so I'm going to go 1, 2, 3. That's going to change it by 3. I'm going to change my rise by 2. So that means I'm going to go up 2, 1 and 2. So we can track this motion as saying I'm going over 1, 2, 3. I'm changing my run, right, by 3, and I'm going up my rise by 2. So all in all, this would be one of the points that is on my line. Is there another point on the line? Of course, there's an infinite number of points on my line. I could do this entire process again, and I could say I'm going to go over 1, 2, 3, and I'm going to go up 2 more. So that would be up 2 more, and that would be the point right about here. This would also be a point that's on the line. But notice that I'm connecting all of these lines, or all these dots. So that means that all of these points in between here also work. For example, this one here would be if I went over 1, 2, and then I had to go up a certain amount and still maintain this slope. I wonder what that would be. So let's play around a little bit. I know that all of these points have the ratio of going up 2 every time they go over 3, and I'm curious about this point right here. This point was when I went over 2 from 0, so let's see if I can put that in. That would be my x2 is 2, and my x1 is 0. Okay, great. And then my y2 would be the y value of the second point. I don't know what that is. I'll have to leave that alone for right now. And then I have my y1, the y value of my original point. I know that one's 0. Could I find out how high that point is? Well, let's play around. This would be, maybe I'll do a full arrow over here so that I have 2 over 3. I'll just carry everything over, equals, and I can simplify. Y2 minus 0 would be y2, and then 2 minus 0 would be 2. I could even solve out for y2. That would be, let's see, I would need to multiply both sides of the equation here by 2. And that would get me 4 over 3 is equal to y2. And I think that that's it, right? So that must be what this coordinate is right here. I'll draw that in. This point right here must be at the coordinates 2 for my x value, and then 4/3 for my y value. because that would have to be the relationship, the ratio that would occur if I only took 2 of my 3 steps over, is that I would only go 2/3 of my way towards 2, and 2/3 of my way towards 2 would have to be, oh, well, 4/3. Interesting. So we've got this common relationship. And we could even go this way. Let's see if we can find a negative value. So I'm going to extend my line out this way. And maybe I'm curious what my y value is if my x value is -14. So I'm going to take -14 steps on over. Let's see if we could solve that one quickly. So I'll break that one out. That says that I still have this common ratio of 2 to 3. And I know that I'm going to some y value. I don't know what that one is. I'll say y2. And then I am going away from some other point. Should I choose the origin again? I could choose any point. Maybe I'll choose this point right here. Why not? Let's play. That would be 4/3 would be my y1 value. And then my x2 value would be the one that goes along with this point down here. That'd be -14. And then I would have minus, let's see, my x1, if I'm using this point, would be 2. And so let's see if I can solve out for everything there. That would be still 2/3 equals y2 minus 4/3. And then on the bottom, I've got -14 minus 2 would be -16. I could multiply both sides by -16. That would get me -32/3 equals y2 minus 4/3. And then I could add 4/3 to both sides. That would be -28/3 equals y2. Oh, and there you have it. So it seems like I want to figure out when my x value is -14, that would be that my y value must be equal to -28/3. And that would be the height of this point over here. So you can play between all the different points. You can continue to bounce around so long as you're able to keep everything organized in the fraction and you keep the y's associated with the correct x's. You can use any reference point so long as you understand the slope. And the slope is, again, just the ratio. It's the number of steps I'm taking from one towards the other. Kind of fascinating that when you have something that's equal, you can use it in such a creative way. Okay. Now that was sketch a line with a slope of m equals 2/3. We absolutely did that. Notice, by the way, that that was the slope. That was a slope that we used and it went through the origin. In fact, there are an infinite number of lines that have a slope of 2/3. This one would have a slope of 2/3. This one would have a slope of 2/3. They would each go through different points, of course, and we would often call these lines parallel. So parallel lines are going to be lines that have the same slope as each other, and in fact, there's an infinite number of parallel lines. They never cross and they all go through different points. So depending on what the point is that we first use as reference, that slope could get us a completely different set of points that it goes through. Kind of fascinating. Okay, so now let's take a look at here how we might find the equation of a line with all of this. That's where things become a little bit more difficult. So if we want to find the equation of a line, remember again that there's 2 pieces of information that we need. The first thing is we need a point. So let's see what we can do. Let's use a point, and maybe we'll choose a random point here. Well, never mind. Let's start with an easy point, and then we'll use another one. All right, let's find the one that we had drawn originally, this one that went right through the origin. I'm really curious what the equation is of this line. Well, I have an equation that talks about that line. It's the slope one we've been playing with. So what's my point? My point is 0, 0. My slope, my m value, is equal to 2/3, and I'm trying to find an equation for this line. Well, I should always start with something that I know if I'm trying to do any kind of problem solving, and I know that my slope of 2/3 is equal to the ratio between any future point and a past point if I compare the y values and the x values. Well, if I have at least one of the y values and the x values, I can put that in. That'd be 2/3 equals, my y2 would be 0 minus, oops, or do we want to make that our y1? It doesn't really matter, actually, does it? We'll do it as our y2. Yeah, we'll do it as our y1. I'm saying it doesn't matter, but I'm trying to keep the math a little bit simple for now. So we'll say that's our original point. So we'll make it as y1. Again, it doesn't matter. Maybe you've tried doing it the other way. It really doesn't matter. So we'll do y2 minus y1, which is 0, my original point, and then over x2 minus 0. Okay, great. Now that would be any future y value, any future x value that's tied into the same point. What if I want to talk about all of them? Every single one of them? Well, first of all, we can recognize that we can already write this a little bit more simply. We have 2/3 equals y2 over x2. And then what if instead of just talking about the second point and a third point and all these 2's and 3's, I just try to write this without the 2's and 3's? Maybe I just talk about it as being all future y values, all future x values. Okay, I can capture that piece of information. I'll just write that all as 2/3 equals y over x. There you go, I took away the 2. Now I'm no longer talking about a second point, I'm talking about any point in the future. Can I solve out for y the way that we're used to seeing equations? Sure, I'm just going to multiply both sides by x, because right now I have x in the denominator. So that would be y equals 2/3 x. And that would be the equation of the line that we're playing with. Don't believe me? Let's check. We knew here that 2,4/3 was a point that appeared on our line from our construction, and we know that our equation is something that relates all x values and y values that take place on a curve, on a shape. Let's see if this actually works. So we're going to test our equation for our line. Y equals 2/3 x, and we're going to try it with this x value and this y value over here. So let's go ahead and do that for our x value. That would be 2/3 times 2, and then for y it would be 4/3. Is that true? Well, 4/3 is 2 of 2/3, so yeah, I think that's absolutely true. And it works for that solution, it works for the other solutions that we came from, it even works when you put in the origin, the 0, 0. And so what we've created is we've started from a place of logic, and we've started from a place of modeling in something that we knew was true. We created a relationship, and then from that relationship, we were able to describe every single x value we wanted, because that's what we were really doing anyways. So let's see if we can find 3 more points located on this line. Well, now that we have the equation for this line, y equals 2/3 x, let's pick some points. So maybe I will choose, and I'll organize this in a table to make it nice and pretty. So I'll choose some x values. Maybe I'll choose -10, maybe I'll choose -3, and maybe I'll choose a fun number like pi. Let's plug it in and see what happens. If I put in -10, that's going to be -10 times 2/3 is -20/3. If I put in -3, that would be -3 times 2/3 would be -2. And if I put in pi times 2/3, that would be 2 pi divided by 3. So that means that my 3 points that I found on my line are -10, -20/3, -3, -2, and pi, 2 pi over 3. And there are infinitely more. Any number you want to plug in, you're going to be able to find out where our height is based on that x value. Or if you wanted to figure out some heights or some x values, you could plug in a height and figure out our other value. And this is just one of many lines that has a slope of 2/3. Other equations you could play with, and I'll put this in orange so that you know that this is for a different exploration, but you could have absolutely considered y equals 2/3 x plus 1, or y equals 2/3 x minus, I don't know, 2.8. Any of these numbers would be numbers that have a slope of 2/3, because again, that's how we got this 2/3, is that that's where our slope goes. If you don't believe me, see if you can start off with where would those points be, put them into your equation for your slope. Remember how we started it up just like this one. But if I wanted it to go through a couple of these different points, like I wanted it to go through 1, was that my y value or x value? That's an interesting question. Okay, maybe we jumped too far. We'll come back to that question in a second. Put a little box around it, we'll come back. Okay, so recall that linear equations, we've talked about linear equations before, and we talked about them in a little bit of a, I don't know, we didn't really tell you why they were called linear equations at the time, and I'm not usually a huge fan of that, but it's sometimes fun to do a bit of a reveal. So recall that we normally talked about linear equations as being something of this form, where we have ax plus by equals c, where a, b, and c are just real numbers. So this means number times x plus number times y equals c. Can we find out if this and what we've been playing with, these line pictures, are in fact the exact same thing? Okay, well, let's play around for a moment. Here we go. We know that lines have slope. So we have slope, and we know that that slope is going to be a y2 minus y1 over x2 minus x1. Okay, and we've found a simpler way to write that now. M is equal to And then instead of y2 minus y1, we've said sometimes we can just talk about all future y values and take it in reference to some original point. So what's our original point going to be? Do we want to use a number? Maybe not if we keep it general. Let's talk about our original point as maybe just being, oh, what should we call it? Lowercase d and lowercase e? Okay, so these are numbers. We'll put a little symbol over here to ourselves. This is just some point that I'm choosing to start, some x value, some y value. Okay, so it'd be y minus e, oh, not d, y minus e. I have to make sure I'm subtracting y values from each other. Y minus e over x minus d. And let's see if I can simplify this up a little bit. So I'll simplify this up and say I can get rid of the fraction by multiplying by the entire denominator for both sides. That would be x minus d multiplied by the entire left, and multiplied by the entire right, which would cancel it away. So I have y minus e, no problem. Let's see, what else do I need to do? I could simplify up the parentheses. That would be x times m minus d times m is equal to y minus e. That's working fine. I could get all my y's and x's on the left-hand side. That'd be if I subtracted y from both sides. That'd be xm minus y minus dm equals e. And then let's see, I could get rid of the dm, get that onto the other side. I'm just playing. Xm minus y, I could add dm to both sides, and that would give me e plus dm. And would you take a look at this? I think we've gotten there. If you don't believe me, I'll see if I can explain my thoughts to you. Ax just means some number times x, and we agreed that m is just some number. It's my slope number. So here you are, number times x, no problem. B is just some number, and here you are, I have a number times y. My number is -1. I've got a number times y, that works. And then C is just some number, but you told me that again. E was a number that we had chosen, D was a number we had chosen, and M was a number that we were given. So on the right hand side I have nothing but numbers. So yeah, sure enough, my ax plus by equals c, so long as a, b, and c have numbers, they're numbers that are going to be the exact same as what I would have gotten if I had started from my slope and I had mixed things around a little bit. That's kind of interesting. Maybe we should try that with a number or a problem that actually has numbers. So let's go ahead and take this away. We'll give ourselves some space. So let's take, for example, the y equals 2/3. Let's see what that one might have looked like. So that one, we knew, if we remember, that m was equal to 2/3, and that we had rewritten that as saying that that was going to be, let's see, y minus 0 over x minus 0, right? That was our line that we had used. And so we had then taken that and we had said that that could be, if we multiply x on both sides, that would be 2/3 x equals y. That's where we had ended up in the last problem. How would we have gotten it into this structure? How would we have gotten the x and y's on the same side? Oh, well, let's just get the y on the other side. We'll subtract y from both sides. So it'll be 2/3 x minus y equals 0. And there you have it. Now I've just rewritten it and reorganized it into how we used to look at linear equations. Number times x plus number, -1 in this case, times y equals number, 0 in this case. So there you have it. And you could do this for any linear equation. You could reorganize it to get to the place where it represents its original slope. You could get it back into a place where it's all nice and lined out, where you have variables times numbers equals numbers. Any way that you want to manipulate this is connecting all of these different perspectives that we've been playing with so far. Kind of fun. So we've recognized that there are many different perspectives by which we can view linear equations. We can view them as linear equations where anytime we see a number times a variable plus numbers times variables equals numbers, that is one way of looking at lines. Linear equations, the way we dealt with back in the review chapter. We could look at it as slope equations, the way we were playing with slopes. Those create lines so long as I'm true to the meaning. And so here I'm going to give you a few of these other representations that people are more familiar with that you've probably seen in past algebra classes. If you haven't, no problem, I'm going to show you that again. There's a lot here that it looks like a lot, but it's really not. It's however you want to look at it, and if you don't want to look at it a certain way, just change it. So here we are, the point slope form. This is a very popular one. The point slope form is usually written like this. Y minus y1 is equal to m times x minus x1. Very popular form. Now, let's notice a couple of pieces of information for why it's probably popular. The first thing, notice that it does have your m slope. It has your slope. That's the slope part. Where's the point? It does have a point. The point, and I'll use a different highlighter, let's use orange. The point that it's referring to is that you need to have a point in order to get this y1 and x1 values. Okay, and then it's an equation of a line for all points on a line because again, we have x and y, these variables. So y1, m, and x1, everything that I have highlighted is a number. Y and x that I don't have highlighted, those are variables. Those take the place of any question and any answer I ever want to ask. So is this in fact a line? Let's find out. Okay, we're going to start back with what we were most familiar with. That was slope. So we're going to start with slope, and we said slope is m equals y minus y1 over x minus x1. Notice that I've taken the liberty of getting rid of the little 2's now. Now I'm just going to write it as y minus y1 because I already know that if I have a reference point, that's going to be my first point, and any future point, I'm just going to call it y. This will be my future y, my eventual y. And you can do this. I'm doing nothing but recategorizing titles in my head. There's no rules that say I can't call something one way or call it the other, so I'm going to choose to call it without as many subscripts here. If my y and my x are always going to be these future points, let's just keep them as future points. Okay, no problem. Can I rearrange this equation here to eventually get into this equation up here? Well, I think so. In fact, I recognize that I've got my m, and my m is being multiplied by x minus x1. Maybe I should do that. Maybe I should multiply m times x minus x1. I'll multiply x minus x1 on both sides. So I'll do that to the left-hand side, and on the right-hand side, I've got to do it there as well to keep everything balanced. And if I do it to the right-hand side, what do we notice? I notice that I can actually simplify this up a little bit. X minus x1 can cancel here, and I think I'm left with originally what I was given. M times x minus x1 is equal to y minus y1. Okay, great. So here you have it. The point slope form of a line is, in fact, a slope of a formula for a line because it came from one of our definitions of a line that had a slope and a point, and we integrated that according to our own logic. Great, so that's one way of looking at lines, is using point slope form. Slope-intercept form is a very common one. That's y equals mx plus b. Now this might seem a little bit unfamiliar. B is, by the way, referring to a y-intercept. Let's see if we can pull out that logic. So again, let's start from a place we're most comfortable with. And I'm going to start from the slope equation again, but if you wanted to, you could absolutely start from this equation. Maybe we'll do that in a second. So let's start from the slope equation. That'd be m equals y minus y1 over x minus x1. Here again, I notice that I have m times x, so maybe I want to multiply both sides by x minus x1. So we'll say m equals and I will multiply by x minus x1 on the left, x minus x1. And I'll do that to the right-hand side as well, y minus y1, and I'll multiply it by x minus x1, and I guess I got to keep it exactly how it was, so x minus x1, great. I can cancel. Oh, and in fact, okay, so I'm back to my point slope form of a line. Y minus y1 equals m times x minus x1. Let's see, what else do I need to do to make it look similar? I think I need to get y alone. Notice that y is alone up here. So that means that y is already here. Let's get rid of the minus y1. We'll add y1 to both sides. Okay, so that'll be x minus x1 times m plus y1. I'm going to add it to the right-hand side and the left-hand side equally. That gives me y. That looks pretty good. There's no parentheses in what I'm trying to get to, this equation at the top, so let's see if I can't get rid of the parentheses. That'd be m times x minus m times x1 plus y1 equals y. Okay, well, I've definitely got the mx. I'm guessing all of this is all just numbers. Again, x1's a number, y1's a number, they're points that I was given, m's a number, that's a slope I was given, so all of that must be my b? That seems odd. Let's see if we can make some sense of that. We'll sketch a picture. So if I wanted to do something like an equation of a line that had a slope of 1 and a y-intercept of 2, we know from our original equation we could write that as y equals 2 or slope of 1 and a y-intercept of 2, then we're going to put a slope of 1, here we go, 1, x plus 2. Okay. So that would be that my y-intercept is at 2. We'll put that 1, 2, and then I go up 1 every time I go over 1. So I go over 1, I must go up 1, that's my line, and that's my line. Perfect. Okay, so that's the equation of my line using slope-intercept form, if I'm to believe that it is in fact true. Would it work with everything up here? Let's try it. Let's try it with some numbers. So I've got m. M is going to be 1. So I'm taking all of this. I'll circle it in pink so that we keep it straight. All of this right here, I'm about to make it into 1. Okay, and I will only know that this is legitimate if all of this craziness here at the back end is equal to the same thing as b. Okay, so we've got 1 times x minus m is 1. x1 is, let's see, want to choose a point. Maybe we'll choose this point here, 0, 2. Okay, so x1 would be 0, okay, plus y1 would be 2 in this case. Does that work? I think so. Equals y? That would simplify to x plus 2 equals y, and I think that's the same thing as what we started with right here. Okay, good. So this is, again, an equation of a line, this slope-intercept form of a line. Why would we ever try to write it like this instead of going back to our slope or going back to our point-slope form? Well, I definitely think that it looks a lot simpler than all of this pinkness. I like the fact that it calls out my intercept quite directly, and I like that it just has my slope. Those are two very easy points for me to reference, or two very easy pieces of information for me to reference. So I could see some value here. The point-slope form let me use any kind of point and my slope. The slope-intercept form allowed me to use a very specific point, my intercept, along with my slope. Okay, so that works out quite well. And again, I could probably rewrite it the same way we had the original equations. Interesting. Okay, fine. And then the standard form of a line. Have we done the standard form of a line? We did. Remember, the standard form of a line was this ax plus by equals c. Can I get to this from one of my equations of the line? Well, maybe I'll start this time from my y-intercept, because I've shown my slope-intercept form, because I've shown that everything above is kind of equivalent. Can I connect my slope-intercept form, this y equals mx plus b, into something like this? I need to get it of the form number times x plus number times y equals number. Okay, maybe I need to get my x's and y's on the same side. I'll subtract mx from both sides, and that would get me negative m times x plus y equals b. Oh, and we're done. Look, there you are. M is a number, negative m is a number, times x, plus number times y equals number. And that's exactly the same thing here. Number times x plus number times y equals number. So when you're working through these problems and you're recognizing that really these standard forms and all these variables and these capital letters are not as confusing as they look on the paper, you really want to take a moment back and re-establish the meaning. The standard form just simply says I can recognize that something's linear if all I have in front of me is multiplication, addition, subtraction, and I have no exponents that are above what could be thought of as the power of 1. That's one way to recognize a line. Slope-intercept form is a way to recognize a line by saying I know its y-intercept and I know that every time I take a step over in my x, I'm going to go up a certain amount from my slope. That's another way to recognize a line. The point-slope form says if I recognize that I have one point and that I've associated all future points in connection to that point with the same slope, then that's another way of thinking about a line. And so all of these are just different ways of capturing the idea of saying that I have direction and I have a reference point. And so long as I have those two pieces of information, it doesn't matter how you want to organize it, it's going to tell you the exact same kind of story. So before we go, let's talk about a couple of interesting pieces of information. So what's the slope of every horizontal line? Okay, that's an interesting one. Let's start from a picture again. We'll play. So we're going to draw out a little picture here, and we have a point and another point on a horizontal line. So we're going to draw that one across. Sometimes in my notes I get a little confused as to which of these things that I've drawn is my line or my axes. So sometimes I'll kind of shade in some of these arrows to say that the shaded in are going to be my reference coordinate plane, and then I usually don't shade in my arrows for my line. So if you ever see it written out like this, that's one way that you can kind of keep it straight on your own paper if you'd like. But nonetheless, what would be an example of this horizontal line? oh, this example of this horizontal line, I don't know, maybe I'll say that it came over 4 and it was up 3. So that would be 4 comma 3, and then this one over here would need to be -5, and it would need to be the same height because it's horizontal. So -5 comma 3. What would be the slope here? Slope is m. M is equal to y2 minus y1. Or you could think of it as y minus y1, it doesn't really matter, over x2 minus x1. Really what it just means is a future point minus an original point. And so the future point, pick your point. I don't know which one's future, it doesn't really matter. Maybe we'll choose the left one as the future. That'll be 3 minus 3. And then on the bottom, it'd be our future point would be the -5 minus 4. And so we could solve this out and say 3 minus 3 is 0. -4 minus -5 minus -4 is -9. There we are, equals 0. Okay, so that's the slope of a horizontal line. In fact, that'd be the slope of any horizontal line. If I ever wanted to draw a horizontal line, I could just draw a line through and say that it has a height of, I don't know, maybe the same as the y-intercept, because that would be, it'd have to be that height as well. I could say that it's always going to be some kind of x value, maybe x1 comma b, some b height that could be positive or negative. And over here, I'd have another x2 minus, or x2 comma b for the height of this point down here. Any of these points are all going to have the height of b, so my slope is always going to be a height of b minus a height of b equals 0. Okay, so horizontal lines will always be a slope of 0, and so write yourself a little note here. Horizontal lines have a slope equaling 0. And I think that this makes a little bit of sense if we take a moment, because after all, if I was going to try to go sledding originally on my ski hill, I would probably be wanting to go on something that has a very small slope, a very easy slope, and so that would probably be something that is very small number, and if I had a 0 slope, that would probably be a hill that wouldn't really be a hill, it'd probably just be a flat piece of land, and so this is all kind of making sense. A horizontal line is going to be 0. What's the equation of a horizontal line with the intercept of y equals 5? Oh, well that would be, again, y equals 5 would be, I'm going to draw some kind of line here. It's going to go through the y value of 5. And so that's always going to be, let's see. Oh, but I need the equation of a line. Oh, okay, so let's start back from, what do we want to use? Maybe the y-intercept equation, because I have a y-intercept in my example. That'd be y equals mx plus b. Y equals mx plus b, I could simplify this up. Y, any future y value, would be determined from a slope. My slope is 0, it's a horizontal line. So it's 0 times x plus b. B would be my y-intercept, 5. So all of this would say that y is equal to 0 times x is 0 plus 5 is 5. So y is equal to 5. Well, isn't that kind of interesting? That's like a summary of what we would expect to think for a horizontal line. Is that it's a line where the y value is always 5. The height has to always be the same, because if it's always the same, then it's a horizontal line. It can't go down. If it went down, it couldn't be y equals 5, and it wouldn't be horizontal. All these things tie together in different perspectives. What fun. Okay, what is the equation of a horizontal line with an intercept of y equals b? Oh, well, wouldn't that just be exactly what we had explored 2 questions ago? Y equals mx plus b would be what we started with. This time I'm going to replace b with b. So it'd be y equals, m is 0 because it's a horizontal line. So that'd be 0 times x plus b. I can't put in a number for b, I'll just keep it as b. That would be y equals b. Oh, interesting. So actually saying that it's horizontal and saying that the slope, or that the intercept is y equals b, tells me that all future y values have to be y equals b as well. I have the same information. I ended up just circling back to the same idea that I could have probably figured out just from the information I was given. What fun. Okay, what is the slope of a vertical line? We talked about a vertical line before. It was an undefined slope. Do you remember? Remember again that slope is m equals y2 minus y1 over x2 minus x1. Similar to what we were just talking about for a horizontal line, a vertical line, a line that goes straight up and down, is a line where the x values have to be the same. If the x values weren't the same, then it would tilt a little bit, because I would be changing my x values. I'd be going over a little bit. If I go over to the side a little bit, I'm not vertical. So vertical means the x values are the same. So you think of that as saying that if on the bottom, you have the same thing minus itself. Same thing minus itself on the bottom is going to be a 0. On the top, it doesn't matter what you put. You're always going to get something that's undefined. Okay, so we can't talk about the slope of a vertical line. The slope of a vertical line is always undefined. Well, we can talk about it, we just can't say it's a number, it's an undefined value. So what would be the equation of a vertical line with an x-intercept of x equals 3? That's a tricky question. Okay, well, there's two ways we could approach this. The first way is we could try to think that it'd be the exact same way as the horizontal line. It's just that now the only information I'm aware of is that x value is always equal to 3. So that just means that my equation is x equals 3, because any time that you ever try to choose a point, you can pick any point you want in the world for y. You can go any height you want, but the x value has to always be 3. So this contains all the information you would want. The other way of thinking about it is if we tried to go through the exact same steps we did before. y2 minus y1 over x2 minus x1. I might not be able to talk about the slope, but I can think about this as being that the slope is undefined, meaning that it's a y2 value minus a y1 value over x2 minus x1, where x2 minus x1 is 0. So in other words, that means that what? Oh no, I can't divide by 0, so I can't. Nope, I think that's all. Never mind. I had an idea, but I don't think it's going to work. I think this is really all the information we're going to contain is that x is equal to 3. Y could be literally anything it wants, and if you don't believe me, plot it on a coordinate plane. I'm going to say x equals 3. That's the only thing I need you to be specific about is x equals 3. So if x equals 3, 1, 2, 3, I could pick any y value you want. Maybe I can make it negative, I can make it positive, I can make it huge, I can make it small. But all of that information, if you keep that piece of information true, everything else is going to be true and you will get a vertical line. Kind of crazy to think about. No matter how you want to change your perspective, all we're doing when we're writing equations for lines and equations for circles is trying to figure out what's the minimum amount of information I need to put on the paper such that if you hit it, then you have no choice but to draw exactly what I have in my mind.